It was a dusty afternoon in late spring when James Ellison decided to clean out the wooden crate that had been sitting in his garage for over a decade. The box had belonged to his late uncle, a quiet man who'd once traveled through Nevada collecting rocks as a hobby. James never paid much attention to the collection. They looked like any other rocks. Dull, grayish, some speckled with what looked like sand or metallic flecks. His uncle had labeled them with rough handwriting on masking tape: quartz from Elko, volcanic debris, crushed granite. There was nothing that screamed value. But something about one rock stood out that day. It wasn't the biggest or the shiniest, but it felt denser, heavier than the others. The surface had a greasy luster, and when the sun caught it just right through the garage window, there was a subtle internal sparkle, like light bouncing through glass, not just off the surface. James didn't know much about geology. He just liked tinkering. But something about this rock made him pause. He scratched it lightly with a screwdriver and saw that it left almost no mark. He tried again with a razor. Same result. Curious, he rummaged through a box of tools and found an old piece of glass. With one quick motion, he scraped the rock across it, and to his surprise, the glass scratched deeply. That wasn't typical quartz behavior. Normally, quartz is around a 7 on the Mohs scale, hard enough to scratch glass, but not with such ease and clarity. This fragment didn't just scratch the glass, it tore through it like it was nothing. Unsure, James took out his phone and began searching how to tell quartz from diamond. That's when the rabbit hole opened. He learned that misidentification between quartz and diamond is more common than people think, especially with industrial-grade or rough, uncut diamonds. The key was not just the hardness or appearance but also the crystal habit, luster, and thermal conductivity. Diamonds conduct heat extremely well, unlike quartz. He kept reading, watching videos, comparing his stone to online examples. The greasy luster, the lack of striations, the way it refracted light internally, all signs pointed to one possibility: this wasn't quartz at all. He decided to take it seriously. The next morning, he visited a local gem and mineral shop. The owner, an older gentleman with thick glasses and a jeweler's loop around his neck, examined the stone for a full 5 minutes without saying a word. Finally, he muttered, "Where did you get this?" James explained casually that it was his uncle's, collected somewhere in Nevada. The man took a diamond tester from the counter, pressed it to the surface, and waited. A sharp beep followed. Then he tried a different tester, this time for thermal conductivity, and again, the readings were off the charts. "This," the shop owner said slowly, "is a diamond fragment. Uncut. Likely industrial grade, maybe even part of a larger crystal that fractured naturally. And if it came from surface material out west, someone may have walked over an entire field of these for years, mistaking them for quartz." James felt the weight of the stone in his hand like it had just doubled. He stared at it, speechless. It looked so ordinary, like any rock you'd skip across a pond or toss aside on a hike. But now it had the potential to change everything. And if this one piece had been sitting forgotten in a crate, labeled quartz, what else had been overlooked? Was it possible his uncle had stumbled onto something major without ever realizing? That night, James spread the rest of the rocks across his kitchen table under a bright LED lamp. He re-examined each one. He began to see things differently. The angles, the density, how some stones seemed to glow from within rather than reflect from the surface. Suddenly, his uncle's collection looked less like a hobby and more like a treasure map, where the markers had been misread for decades. Every piece held new possibilities. Some were definitely quartz, others likely granite or mica. But a few had that same density, that same scratch resistance and mysterious shimmer. James contacted a professional gemologist the next day. The appointment was scheduled 2 weeks out. In the meantime, he kept researching, learning how to do basic tests at home with a loop, light box, and cheap diamond tester he ordered online. It became an obsession. He even found an online forum for amateur rockhounds who'd shared similar stories, people who had unknowingly walked past or thrown away stones with legitimate value, thinking they were nothing more than quartz, feldspar, or glassy debris. One man posted about finding a diamond worth over $18,000 embedded in what he thought was sandstone rubble. As James scrolled, he realized how common this mistake really was. The earth hides its riches in plain sight. Without knowledge or the right tools, most people wouldn't know the difference. But with just a bit of awareness, a scratch test, a close inspection under light, or the courage to question a label, someone could stumble upon something life-changing. In mineral identification, one of the most persistent sources of confusion is the misclassification between quartz and diamond, especially in rough, uncut form. Both minerals occur in nature as clear to white crystalline forms, and both are often found in similar geological settings, especially in alluvial deposits and sedimentary gravel beds. However, understanding the fundamental differences between them is critical for anyone interested in prospecting, rock collecting, or even evaluating possible high-value finds at home. While quartz is one of the most abundant minerals on Earth, diamond is not. Their chemical structures, physical properties, and commercial value differ dramatically. The most important distinction starts with hardness. On the Mohs scale, which rates minerals from 1, softest, to 10, hardest, quartz ranks at a 7, while diamond ranks at a 10, the hardest known natural substance. This difference is not marginal. A diamond will scratch anything below it on the scale, including glass, quartz, steel, and even other gemstones. Conversely, quartz can scratch glass but will never scratch a diamond. One of the most practical and commonly used field methods is the scratch test. Using a steel file, knife blade, or a piece of glass, the suspected material can be scratched to observe resistance. If a rock scratches glass effortlessly and cannot be scratched back by a steel tool, it's worth deeper investigation. Another essential property is luster. Quartz has a vitreous or glassy luster, meaning it reflects light much like common window glass. Diamond, however, exhibits an adamantine luster, a unique sparkle that's more intense and brilliant, especially when rotated under light. Even in rough form, diamond fragments can display a greasy or oily surface that doesn't occur in quartz. This subtle difference is often overlooked, especially in cloudy or weathered specimens. Under magnification or direct sunlight, diamond tends to shine from within, whereas quartz only reflects light on its surface. Refractivity is also a key factor. Diamonds possess an incredibly high refractive index, causing light entering the crystal to bend more dramatically and bounce around inside before exiting. This internal reflection creates the classic fire or dispersion effect seen in cut diamonds. Though this fire is mostly observed in faceted stones, the same property causes rough diamonds to shimmer even in their natural state. Quartz, with its lower refractive index, lacks this depth of brilliance. When rotated in bright light, quartz may flash slightly but not sparkle internally. Another vital test is thermal conductivity. Diamonds are exceptional conductors of heat. In fact, they are the best natural heat conductors known, a property used in specialized testing tools. A basic diamond tester utilizes a small metal probe and measures how quickly heat dissipates from the tip into the stone. Quartz, by contrast, is a poor conductor and will show no such thermal response. This is one of the most definitive tests for rough diamonds and is commonly used in pawnshops, gem labs, and even portable kits for field work. Crystal structure also helps differentiate the two. Quartz forms in a hexagonal crystal system and often shows prismatic shapes with striations, fine parallel grooves on the crystal faces. These striations are a visual clue that instantly rules out diamond, which never displays them. Diamonds crystallize in the cubic system, frequently forming octahedrons or rounded shapes when weathered. If a clear stone has visible striations along flat faces, it is almost certainly quartz. If the stone lacks those markings and has more geometric or compact shapes, further tests may be justified. Density, or specific gravity, is another reliable indicator. Quartz has a specific gravity of about 2.65, meaning it feels relatively light for its size. Diamonds are denser, with a specific gravity around 3.5 to 3.53. While this might not be obvious to the untrained hand, when comparing two similar-sized samples, the heavier one may be worth a closer look. In field conditions, this can be tested using a water displacement method with a graduated cylinder and an accurate scale. Though more cumbersome, it provides helpful supporting data alongside other identification steps. Beyond physical testing, understanding the geological context of the find is crucial. Quartz can be found almost anywhere. It is formed in igneous, metamorphic, and sedimentary environments. Diamond, however, forms deep in the Earth's mantle under extreme pressure and temperature, only reaching the surface through kimberlite or lamproite pipes. That said, in eroded alluvial settings, riverbeds, gravel layers, or glacial till, diamonds can appear far from their original source. In these areas, any unusually hard, dense, translucent material deserves special scrutiny, especially if found near known kimberlite regions or areas with historic placer mining. It's also important to address inclusions. Most quartz samples are fairly transparent or cloudy, often containing visible internal fractures, bubbles, or thread-like inclusions. Diamonds, even in rough form, may contain inclusions too, but they usually look different, often appearing as black specks, carbon, needle-like structures, or cloud patches. Using a loupe or basic microscope, a trained eye can detect these characteristics. In gem labs, more sophisticated imaging and spectrometry can identify the stone conclusively, but basic inspection can already raise enough suspicion to seek expert evaluation. One final but often ignored factor is UV fluorescence. Diamonds often fluoresce under ultraviolet light, typically blue, but sometimes yellow, green, or orange. This effect varies by origin and type, and not all diamonds fluoresce. Quartz, on the other hand, rarely fluoresces under UV unless it contains impurities or is coated. A portable UV light can be used as a quick screening method, especially in field conditions or home analysis. It won't confirm a diamond, but it can be part of a broader toolkit. In summary, while quartz and diamond may appear similar at first glance, a combination of hardness, luster, refractivity, thermal conductivity, crystal structure, density, inclusions, and UV response can help reliably differentiate the two. For rock collectors, amateur prospectors, and even curious individuals cleaning out old boxes of stones, knowing these signs can mean the difference between tossing away a rare discovery or identifying a stone of real value. The Earth doesn't label its treasures. That's the job of the observer, and with the right knowledge, almost anyone can become one. Once a diamond fragment is identified and confirmed through thermal conductivity, refractivity, and hardness tests, the next logical step is to consider the geological implications of its origin. Misidentified diamond fragments are not necessarily isolated events. In fact, they may represent overlooked indicators of diamond-bearing regions, especially in terrains where the presence of kimberlite or lamproite pipes has never been formally explored. Understanding how diamond fragments end up mixed with quartz-rich gravels requires attention to both geological processes and human error in field classification. Diamonds reach the Earth's surface through deep volcanic eruptions that form vertical pipes of igneous rock, primarily kimberlite and, less commonly, lamproite. These structures act like geological elevators, transporting material from the mantle to the crust in explosive events. Over time, erosion breaks down these pipes, scattering diamond fragments across riverbeds, alluvial plains, and sedimentary deposits, often far from the original source. Once separated from their matrix, diamonds are subjected to the same natural transport systems as quartz, feldspar, and other common minerals: rivers, glacial movement, and wind erosion. This leads to a geological context where diamond fragments appear alongside low-value rocks, often visually indistinguishable without close analysis. In such environments, visual misidentification is extremely common. Quartz is so ubiquitous in sedimentary systems that any transparent or translucent fragment is usually assumed to be quartz by default. In field surveys, prospectors often rely on visual inspection and familiarity with local geology, but this creates blind spots. A field geologist trained to expect quartz and feldspar in a certain terrain may not question the identity of a denser, light-refracting stone. Add decades of accumulated assumptions and underfunded regional surveys, and the result is entire landscapes being passed over for diamond evaluation. This is especially likely in regions historically mined for other resources, like gold or silver. Miners working placer deposits for fine gold often discard larger pebbles, unaware that 1 in 1,000 could be a diamond fragment. In regions with no formal history of diamond mining, like parts of Nevada, Idaho, or even inland California, these fragments are rarely tested, cataloged, or followed up. This creates a perfect environment for misidentified diamond material to accumulate in private collections, university samples, or even landscaping rock sold commercially. The industrial consequences of this are significant. Most natural diamonds are not gemstone quality. They are used in cutting tools, drill bits, abrasives, and heat-conducting films. These industrial diamonds are typically sourced from either deep mining operations in Africa and Russia or from synthetic processes using high-pressure, high-temperature machines, HPHT, or chemical vapor deposition, CVD. However, if natural diamond fragments are being overlooked in certain regions, there's a potential to reduce reliance on synthetic or imported material, especially if economically viable concentrations are confirmed. The key lies in bulk sampling and systematic testing. A diamond discovery doesn't always begin with a brilliant gem. It often begins with an overlooked fragment that triggers a more detailed analysis of the surrounding sediment. Modern exploration techniques now combine drone-based mapping, heavy mineral concentrate testing, and portable spectroscopy to scan riverbeds and surface gravels for anomalies. By filtering out common silicates and focusing on minerals with high specific gravity and thermal conductivity, geologists can identify diamond indicator minerals such as pyrope garnet, chromium diopside, and ilmenite, all of which often co-occur with diamonds. When such indicator minerals are found, they suggest the possibility of a nearby primary source. At that point, exploration moves from alluvial zones to possible pipe structures, even if deeply buried. Ground-penetrating radar, electromagnetic imaging, and geochemical soil testing can help narrow down targets. But all of it starts with a single assumption being challenged. What if this isn't quartz? For individual rockhounds or amateur collectors, this has enormous implications. It means that in certain geologically favorable regions, what looks like a simple hobby, collecting translucent rocks from dry creek beds, might actually be brushing against one of Earth's most valuable minerals. The same applies to antique rock collections passed down through families or stored in university cabinets. If they were cataloged before the modern surge in amateur diamond detection methods, they might contain overlooked specimens. Many people assume diamonds are only found in Africa, Canada, or Siberia, but the truth is more complex. While those regions have commercial-grade operations, the geological conditions that form diamonds exist globally. The United States has kimberlite pipes in multiple states, including Wyoming, Colorado, and Arkansas, the latter being home to the Crater of Diamonds State Park, a location where ordinary citizens have found multiple carat stones lying on the surface. The only difference between a known diamond site and an unknown one may be whether anyone ever stopped to question the quartz. Ultimately, the failure to recognize rough diamonds in the field comes down to two factors: expectation bias and lack of testing. Most stones aren't tested because most people believe they already know what they're looking at. They see quartz and move on. But as shown through repeated field reports, amateur discoveries, and reclassified samples, the potential for misidentification is real, and more widespread than previously assumed. The line between a common rock and a diamond fragment is often just one test away. In addition to physical and geological indicators, chemical analysis can further differentiate diamond fragments from quartz and provide greater clarity in cases of ambiguity. While most amateur tests focus on hardness and thermal conductivity, professional laboratories use Raman spectroscopy, X-ray diffraction, XRD, and Fourier transform infrared spectroscopy, FTIR, to identify the molecular structure of a sample. These methods can definitively confirm whether a crystal lattice matches that of carbon in the cubic system, diamond, or silicon dioxide in the hexagonal system, quartz. For anyone considering the commercial potential of a suspected diamond fragment, these tests are not just helpful, they're essential. Raman spectroscopy, in particular, is a non-destructive technique that measures how laser light interacts with the molecular vibrations of a sample. When used on diamond, it produces a sharp, distinct peak at 1332 cm superscript 1, a signature not shared by quartz. This allows even cloudy or opaque specimens to be accurately identified without the need for cutting or altering the stone. The advantage of this method is its speed and precision. A small handheld Raman spectrometer can confirm diamond presence in seconds with minimal sample preparation, making it ideal for field verification. X-ray diffraction, on the other hand, works by directing X-rays at a crystalline sample and analyzing the diffraction patterns that result. Each mineral produces a unique pattern based on its internal atomic arrangement. Diamond, with its cubic structure, yields a pattern entirely different from that of quartz. While this method requires laboratory-grade equipment and expert interpretation, it remains one of the most conclusive ways to authenticate a sample, especially in cases where the stone is embedded within other materials or partially weathered. Fourier transform infrared spectroscopy adds another layer of insight. By analyzing the absorption of infrared light, it can detect impurities within the crystal, such as nitrogen, boron, or hydrogen. These inclusions not only help confirm a diamond but can also reveal information about its origin, whether it formed naturally in the Earth's mantle or synthetically in a lab. Natural diamonds often contain trace nitrogen grouped in specific patterns, while synthetic diamonds produced by HPHT or CVD processes show different spectral characteristics. This is particularly important for legal certification and resale, as natural diamonds hold far more market value than synthetic ones, even when visually similar. Once a fragment is confirmed as diamond through such advanced testing, questions of provenance and potential value arise. Gem-quality diamonds are judged based on the 4 Cs: carat, color, clarity, and cut. But in the case of rough fragments, the initial assessment focuses more on carat weight, crystal integrity, and the feasibility of cutting. Industrial diamonds, even when not suitable for jewelry, still carry significant value due to their hardness and utility in tooling. A single 3-carat industrial diamond can be worth hundreds of dollars. Larger or clearer fragments may fetch thousands, and that's before any evaluation for faceting. Beyond individual fragments, the presence of multiple misidentified diamonds in one region suggests potential for small-scale prospecting. In areas where surface mining is permitted, even individuals without corporate backing can file mineral claims and begin legal collection under state or federal guidelines. In the United States, agencies like the Bureau of Land Management, BLM, regulate such claims, and in some cases, a single sample with commercial grade value can justify exploration permits and attract investment. The cost of filing and maintaining a claim is relatively low compared to the potential return, particularly if the region shows additional signs like indicator minerals, historical volcanic activity, or unexplored sedimentary basins. One of the most overlooked advantages for modern prospectors is access to satellite imagery and open-source geological data. Free platforms like USGS Earth Explorer or state geological databases offer high-resolution imaging, topographic maps, and historic mineral reports. By cross-referencing these tools with known diamond-favorable structures, like ring complexes, rift zones, and uplifted cratons, individuals can identify likely target areas for exploration. Some enthusiasts even use machine learning models to correlate terrain data with known diamond deposits globally, creating predictive overlays for regional surveys. Digital tools aside, the importance of proper sample handling cannot be overstated. Too many potential diamond fragments are compromised by improper cleaning, cutting, or storage. For instance, using harsh abrasives or high-speed grinders on a specimen can fracture its surface, obscure inclusions, or even cause it to chip. Similarly, storing rough stones in plastic bags with other rocks can lead to scratching, contamination, or accidental disposal. The best practice is to wrap each suspect fragment individually in soft cloth, label it clearly, and photograph it under multiple lighting angles. If thermal or conductivity testing is being done, documentation of each result ensures a reliable chain of information for future appraisal. In communities of amateur collectors, a growing trend is the formation of local verification groups. These informal clubs often share tools like diamond testers, UV lights, or even microscopes, pooling knowledge and experience to increase identification accuracy. Online platforms like Reddit's r/rockhounds, gemology forums, and Facebook rockhounding groups have also become rich sources of real-world case studies, test results, and success stories. Many of the recent rediscoveries of misidentified diamonds started not in labs or auctions, but in these digital communities, where someone finally asked the right question about a rock that didn't quite fit in. There's also growing interest from the academic sector. Universities with geology departments are increasingly interested in collaborating with private citizens to examine unusual samples. This is partly due to the increasing use of crowdsourced data in mineral mapping, and partly because many of these unusual finds fall outside the scope of traditional fieldwork. Bringing a verified diamond fragment to a local university lab can not only help confirm its identity, but may also contribute to ongoing research into previously undocumented diamond occurrences in North America. Altogether, what begins as a curiosity, a single stone that feels different, can open the door to an entirely new understanding of a region's geology. More importantly, it demonstrates how critical observation, basic field tools, and public data access can empower anyone to participate in serious mineral discovery. Misidentified diamond fragments are not just geological anomalies. They're a testament to how much remains hidden in plain sight, waiting for someone to look closer and question what they've always been told is just quartz. Despite the increasing availability of tools, data, and community support, the broader issue persists. Most people simply don't believe that a valuable material like diamond could be hiding in plain sight. This skepticism is rooted in how society views geology and mineral wealth as something distant, controlled by corporations, or locked away in remote locations under extreme conditions. The idea that an uncut diamond could be sitting in a driveway, trail, or old storage box seems far-fetched to the average person. And yet, real-world cases continue to prove otherwise. The misidentification of diamonds as quartz or glass is not rare, it's just rarely corrected. One contributing factor is that the average person is never taught to look for diamonds in raw form. In popular culture, diamonds are always portrayed as cut, brilliant stones sitting on rings or necklaces. This mental image blinds people to the appearance of rough diamonds, which can be cloudy, oddly shaped, and surprisingly dull at first glance. Many resemble broken glass, pebbles, or common quartz chunks. Without a trained eye or proper tools, they are nearly impossible to distinguish in the field. Worse, informal rock collectors may discard them before testing, assuming they are junk crystals or uninteresting inclusions in river stones. The visual similarities to quartz become a trap, and valuable fragments are lost in the process. Furthermore, in many school systems, geology is underrepresented or simplified. Children may learn that diamonds are hard and form deep in the earth, but they are rarely taught how to identify raw minerals. Even in university geology programs, diamond recognition may be limited to theoretical lectures or lab-controlled samples. This leaves a gap, one that amateur rockhounds and citizen scientists are beginning to fill. But without outreach and public education, most people won't even think to test what they find. As a result, countless fragments are likely being overlooked every year. Some of the most surprising diamond discoveries have occurred in exactly these overlooked contexts. One documented case involved a man in Arkansas who found what he thought was a piece of quartz while walking across a freshly plowed field. It turned out to be a 4.38-carat yellow diamond, worth tens of thousands of dollars. In another instance, a woman who frequently walked the same trail in Colorado found a translucent stone near a creek and kept it in her windowsill for years, thinking it was a neat piece of crystal. Only after watching a geology documentary did she decide to test it. It was a 2.7-carat diamond. Neither of these individuals were trained geologists. They were observant, curious, and open to the possibility that their assumption, "this is just quartz," could be wrong. These examples highlight a powerful reality. A misidentified diamond fragment only remains worthless for as long as it's misunderstood. The moment someone tests it, asks the right question, or brings it to a lab, everything changes. And because rough diamonds are naturally formed, not manufactured with barcodes or markings, their value is invisible until uncovered. No stone announces itself as valuable. Its identity must be revealed through deliberate observation and testing. The barrier, therefore, is not scarcity, but knowledge. For those who want to begin identifying stones in their own environment, the process doesn't require expensive lab access. A basic kit can include a jeweler's loupe, diamond tester, glass plate, UV flashlight, scale for weight, and access to online databases or communities. With those few tools, it's possible to begin sorting stones into categories: low hardness, high luster, greasy surface, visible striations, high density. Over time, patterns emerge, and fragments that don't fit the quartz profile stand out. Each one becomes a candidate for further testing, documentation, and possibly formal appraisal. Even modern smartphones can aid the process. By photographing a stone under direct and indirect light, users can analyze how it refracts, examine surface texture, and compare images with verified samples online. Free mobile apps also simulate spectrometer readings based on visual and UV behavior. While not as accurate as professional equipment, they offer accessible tools for initial screening. Combined with basic tests like scratch resistance and heat conductivity, they form a solid foundation for amateur identification efforts, especially in remote areas or during travel. Another technique growing in popularity is density estimation using water displacement. By placing a stone in a graduated container of water and measuring the volume it displaces, then weighing it precisely, one can calculate its specific gravity. Quartz, as noted earlier, has a density of about 2.65 g/cm superscript 3, while diamond ranges between 3.5 and 3.53 g/cm superscript 3. A significant deviation toward the higher end may indicate further investigation is needed. Though rudimentary, this method has helped many hobbyists flag unusual specimens for professional review. Yet perhaps the most important habit any prospector can develop is learning to question default assumptions. When someone picks up a stone and assumes it's quartz, simply because it looks like quartz, they are skipping the scientific process. The discipline of geology is built on observation, hypothesis, and testing. Dismissing a stone based on surface-level appearance alone goes against those principles. It is better to treat each unknown sample as a potential anomaly until proven otherwise. This doesn't mean believing every stone is a diamond, but it does mean believing that some might be. This mindset shift is at the core of many recent rediscoveries. People began to ask, what if I was wrong? What if that old box of rocks in the garage isn't worthless? What if the stone I found on vacation wasn't just a souvenir, but a clue? That kind of curiosity drives scientific discovery and, in the case of diamonds, can change lives. Because the truth is simple, most diamonds don't look like diamonds until someone proves they are. In the growing world of citizen geology and amateur prospecting, that proof begins with a moment of doubt, a tool in hand, and the willingness to look again. It's not about luck. It's about learning to see what's already there. As more individuals begin to test and re-evaluate stones in their possession, a recurring pattern is emerging. Many of these so-called quartz samples are turning out to be something entirely different. In rural areas, old collections passed down through families are being re-examined. What was once dismissed as decorative or insignificant is now being scrutinized under modern light, revealing unexpected density, greasy luster, and unmatched hardness. The misidentification is not always dramatic. Sometimes, it's subtle. A slightly heavier than expected stone, a glint that appears only under angled light, or an unusual reaction to heat. These faint indicators are often the only clues that what's in hand is not quartz, but a diamond fragment. One of the strongest catalysts in this growing movement is the realization that high-value materials do not always present themselves in pristine or obvious forms. Rough diamonds, particularly those found in eroded environments or glacial till, often appear weathered, coated in mineral films, or broken into irregular shapes. This contradicts popular expectations, where diamonds are imagined as flawless and brilliant. As a result, even skilled hobbyists may overlook or discard valuable pieces, believing their appearance disqualifies them from being diamonds. But in reality, many commercially relevant diamonds, especially those used in industrial applications, are never cut or polished. They're used as is, in their raw form, and their worth is defined by their physical properties, not aesthetic perfection. Moreover, the methods for verifying these properties have become more accessible. Whereas lab-grade testing was once restricted to institutions or jewelry professionals, it is now possible to carry out comparative assessments with minimal investment. Handheld thermal conductivity devices, digital scales for density testing, and UV lights are all affordable tools now commonly used by amateur prospectors. Their role is not to confirm gem-grade quality, but to flag samples for further expert review. In many cases, this is exactly what's needed. A rock that tests positive for diamond conductivity and lacks quartz striations, while being denser and more light-reactive than quartz, deserves professional evaluation, regardless of how plain it looks to the eye. The wider implication of this shift is that untapped micro-deposits may exist across regions previously considered non-viable for diamond presence. The traditional diamond-producing regions of the world, such as Botswana, Russia, and Canada, were established after extensive exploration programs, geological mapping, and decades of trial and error. But in countries like the United States, many remote or privately owned lands have never undergone such intensive analysis. If just one fragment is discovered in a surface sample, it suggests the presence of a transport path or a larger, weathered system that may have distributed diamonds over time. In this way, a misidentified stone isn't just a rare event, it's a geological signal. This potential is especially important in areas with high erosion, seasonal flooding, or historic volcanic activity. Alluvial systems are natural collectors of denser materials, and diamonds are commonly deposited alongside gold, magnetite, and garnets. Prospectors already familiar with panning for gold may be in an ideal position to start identifying diamond fragments. The physical process is similar. Concentrate heavy materials, observe particle behavior, isolate unusual crystals. But while gold is recognized instantly by its color and malleability, diamonds require more patience. They blend in until they don't. There are also broader environmental and economic implications to consider. As demand for diamonds, particularly industrial and thermal grade, continues to rise, locating domestic sources becomes increasingly relevant. Mining operations are expensive and often controversial, raising environmental concerns and creating geopolitical dependencies. If diamonds can be identified in surface-level deposits, without the need for deep excavation, it may open doors for small-scale, low-impact extraction. This doesn't just apply to commercial entities. Independent landowners with verified samples on their property may be eligible to file for mineral rights, lease to exploration firms, or partner with geological institutions. The legal and regulatory path for this varies by country and region. In the United States, the Bureau of Land Management, BLM, governs claims on public land, while private landowners retain full rights to any minerals discovered beneath their soil. If a diamond-bearing sample is confirmed, and it came from a specific location, the finder can legally register a claim to explore and extract additional material. This process begins with a sample report, followed by an assessment of the surrounding area. A single misidentified fragment can become the entry point into a larger survey project, one with scientific, financial, and even historical significance. Meanwhile, gemological laboratories are increasingly reporting unusual submissions from amateur collectors. These samples, sent in from farms, hiking trails, and even gravel driveways, often arrive with little context, just a note stating, "I think this might be something." In some cases, they're confirmed as quartz or feldspar. But in others, they've turned out to be low-color industrial diamonds, diamond-tipped fragments, or parts of twinned crystals. These are not flukes. They're evidence that overlooked zones hold more than previously believed, and that public awareness is beginning to catch up with scientific reality. For those willing to approach the process methodically, the next steps are clear. Create a controlled sorting environment. Use consistent lighting and surface materials to examine each stone. Label and document every piece that displays unusual hardness, density, or luster. Prioritize stones that resist abrasion, display internal light patterns, or test positive for heat conductivity. Avoid the temptation to clean aggressively or cut into specimens before they've been properly assessed. Many valuable features, including crystal growth patterns and surface characteristics, can be damaged by well-meaning but excessive handling. Above all, trust your data. If a stone consistently scratches glass, registers on a diamond tester, weighs more than quartz of the same size, and exhibits no striations, it is not behaving like quartz. While visual appearance may still cause doubt, the material science doesn't lie. A single stone that meets multiple markers deserves further analysis, no matter how unimpressive it may look. Because in this field, the most valuable discoveries are often the least flashy, until proven otherwise. And that is the fundamental shift happening now. The barrier to discovery is no longer access to tools or education, but belief. The belief that valuable things can be found by ordinary people, in ordinary places, using simple methods. The belief that just a rock might be a lot more, and that every misidentified fragment could be the beginning of something much larger. While belief and curiosity are the starting points, validation remains the bridge between suspicion and discovery. In cases where a potential diamond fragment continues to defy the expected behavior of quartz, resisting scratching, transmitting heat instantly, or revealing dense optical properties, the next step is formal analysis. But many people hesitate here. Some fear the cost, others the possibility of embarrassment if the stone turns out to be worthless. Yet what often goes unrecognized is that professional gem labs and university geology departments not only expect such submissions, they rely on them to build databases of regional anomalies, update mineral maps, and refine exploration models. In other words, submitting a suspected diamond is not an inconvenience to experts, it's a contribution. When submitting a sample, documentation is key. Experts will want to know the location it was found, any prior testing done, even at home, and visible features observed under magnification or UV light. Including photos, scratch test results, and density calculations can help speed up the review process. It's also important not to alter the stone before submission. Any polishing, reshaping, or cleaning with abrasives can damage or distort crucial evidence, such as natural etching patterns or mineral associations on the surface. These details are often what allow gemologists to differentiate natural diamonds from lookalikes like moissanite, zircon, or high-lead glass. Once in the lab, samples typically go through a tiered analysis. The first step is visual and tactile inspection under controlled lighting. If a specimen passes this stage, it may then undergo refractive index testing using a refractometer and thermal or electrical conductivity measurement. Stones that behave unusually are flagged for advanced study. Raman spectroscopy confirms carbon crystallography. FTIR may identify nitrogen aggregates. In rare cases, cathodoluminescence imaging or scanning electron microscopy is used to examine the internal growth structure and surface history of the stone, tools typically reserved for research-grade investigation, but increasingly applied to field samples as interest grows. The outcome of these analyses often surprises even the experts. In recent years, there has been a measurable uptick in confirmed natural diamonds found in unexpected U.S. regions, not in deep mines, but in surface samples sent in by farmers, hikers, or amateur collectors. This trend is prompting geologists to revisit old assumptions about where diamond formation and deposition can occur. The growing understanding is that erosion, glacial transport, and secondary deposition can distribute diamond fragments far from their volcanic sources, hiding them in terrains traditionally overlooked. In such regions, quartz remains the dominant mineral visually, but with persistent testing, outliers are beginning to emerge. These findings aren't just geological curiosities, they have practical and economic consequences. With the global diamond industry facing scrutiny over environmental and ethical concerns, there is increasing demand for locally sourced, traceable stones. Consumers want diamonds with verified origins, mined under transparent and responsible conditions. A rough diamond found in a rural creek, verified and cut in a local facility, carries a narrative of ethical sourcing that many buyers actively seek. For small-scale finders, this means a chance not just for financial reward, but for participation in a new model of mineral discovery, one rooted in community, transparency, and ecological responsibility. In addition, these discoveries can lead to increased educational engagement. Schools and universities located near sites of confirmed diamond fragments often partner with geology departments to host field days, citizen science initiatives, or mineral fairs. Students gain hands-on experience with testing methods, learn to identify minerals in the field, and see the value of scientific curiosity. Some of these programs have already resulted in new finds. In Tennessee, a university-sponsored summer geology program led to the discovery of 3 microdiamonds in material that had previously been classified as mica schist. The stones were tiny, too small for cutting, but their presence rewrote part of the local geological map. Meanwhile, online communities continue to democratize the process. With platforms like YouTube, Reddit, and Discord, thousands of people now share test results, compare photos, and provide second opinions on suspected stones. In some cases, trained geologists join these discussions, offering insight that would once have been limited to academia. A single user uploading macro shots of a strange stone can now receive input from professionals, collectors, and enthusiasts around the world within hours. This real-time feedback loop accelerates the identification process and helps educate a wider public. The tools and knowledge are no longer confined to institutions, they are embedded in the daily habits of curious individuals everywhere. Still, amid this surge in interest, it is vital to maintain a cautious mindset. Not every translucent rock is a diamond. Nature offers a wide range of imitative minerals. Topaz, zircon, spinel, and even high silica glass can behave similarly in isolated tests. That's why cross-verification matters. No single test, not even conductivity, should be considered conclusive. Instead, a checklist of behaviors must be satisfied consistently: resistance to scratching, high thermal conductivity, absence of crystal striations, higher than quartz density, lack of cleavage planes, greasy or adamantine luster, and positive spectral response. The more boxes a sample checks, the higher the probability it is diamond, but the full picture only emerges through accumulation of evidence. Ultimately, what this movement reveals is not just the existence of overlooked diamonds, but a deeper truth about how discovery works. It's not just about finding something rare, it's about seeing the familiar with new eyes. Quartz is so common, so visually dominant, that anything resembling it is usually dismissed without question. But by challenging that assumption, by asking, what if this isn't quartz? People are uncovering not just stones, but stories. Stories of persistence, skepticism turned curiosity, and the quiet thrill of being proven right after everyone else walked away. The final piece of this journey doesn't lie in the stone itself, but in what it teaches. Every misidentified diamond fragment is a physical reminder that value, in its rawest form, doesn't always announce itself. It can be dull, dusty, and nearly invisible to the untrained eye. It can sit on a shelf for years, mistaken for something common. It can be dismissed by experts, thrown into garden beds, buried in old crates, or forgotten at the bottom of a bucket. But when someone decides to challenge that label, to ask, what if? The transformation begins. Not just of the rock, but of the entire way we approach the material world. This shift in mindset represents something bigger than mineral identification. It reflects a growing movement in society toward reclaiming personal agency in exploration, science, and value recognition. The tools are no longer restricted to labs and corporations. Anyone with access to basic testing devices, online communities, and educational resources can begin this process. The democratization of knowledge and instruments has changed the landscape of discovery forever. And perhaps more importantly, it has redefined who gets to participate in that discovery. The truth is, diamonds don't need to be large or flawless to matter. Many of the most impactful finds in the past decade have been small, under 3 carats, rough, cloudy, or incomplete, but their implications were enormous. Not because of their market value, but because of what they revealed about where diamonds can be, and who can find them. They prompted remapping of regions, follow-up explorations, mineral rights filings, and entire shifts in how geological potential is measured. They forced geologists to revisit old territories with new data. They gave individuals the chance to be at the center of scientific and economic events, not just spectators to them. For homeowners, hobbyists, and farmers who might unknowingly be sitting on overlooked material, this is more than a curiosity, it's an invitation. Every gravel driveway, every riverbank, every pile of decorative stones or glacial till could hold something unrecognized. It's not about chasing fantasies or imagining treasure in every rock. It's about training the eye, applying simple tests, asking the right questions, and remaining open to being wrong, and then right. Because the true barrier to discovery is never geology. It's the assumption that what we see is all there is. Even professional sectors are starting to recognize this. Insurance companies, auction houses, and private appraisers are quietly updating internal policies after several publicized cases of amateur discoveries. Items once dismissed as costume or decorative are now being screened more thoroughly. Jewelry with unattributed stones is being reappraised. Some collectors are revisiting their inventories and resubmitting pieces previously labeled as quartz cluster or decorative crystal. The line between hobby and profession is blurring, and the respect for amateur contributions is rising. In some cases, these finds are becoming catalysts for personal reinvention. Stories have emerged of individuals who, after verifying a single diamond fragment, went on to start gem identification services, prospecting YouTube channels, educational workshops, or even small-scale mining operations. Others have donated their finds to universities, collaborated on academic papers, or participated in documentaries. These aren't stories of overnight riches or fantasy. They're stories of people who decided that curiosity was worth following, and that doubt was worth exploring. Their diamonds weren't just physical, they were symbolic of what happens when people reclaim their ability to see. But for every confirmed discovery, there are still countless stones left untested, lying in drawers, resting in gardens, waiting in jars, passed over on hiking trails. This isn't a call to panic or dig through every box in desperation. It's a reminder that value isn't always loud, that it can be quiet, that it can sit still for decades, labeled incorrectly, until someone comes along with new knowledge, a sharper tool, and a fresh perspective. And sometimes, all it takes is that perspective to rewrite the worth of something entirely. As public awareness grows, so does the opportunity for more discoveries. Not just of minerals, but of confidence, skill, and connection. People begin sharing more, testing more, learning together, and building community around curiosity. The story of misidentified diamond fragments isn't just about geology. It's about empowerment. About returning the power of observation and questioning to the individual. About realizing that authority can be challenged when evidence supports it. And about celebrating the quiet triumph of being right when everyone else walked past the same rock. So if you have a stone that feels too heavy, that won't scratch, that glows strangely in the light, or that simply won't leave your mind, test it. Not because it's guaranteed to be a diamond, but because it might not be quartz. And that difference, small as it seems, could open a door not just to a mineral discovery, but to a shift in how you view the world around you. Because this isn't just about geology. It's about the possibility that something valuable is already in your hands, and has been all along.